Hello everyone, this is the week 6 of the TA session of Structure Analysis 1 taught by Professor Amit Shaw. I am Trisha Chakraborty. I am one of the course teaching assistants. I am a PhD student at the Indian Institute of Science, Bangalore. We start with a brief recap of the weeks before. In week 1, we started with the basics of structural analysis, the types of internal forces, common classification of elements and boundary conditions, structural indeterminacy, and bending moment and shear force diagrams. The common types of internal forces are bending moment, shear force, torsional moment, and axial force. And elements we generally classify as beams, trusses, frame elements. And there are various boundary conditions we encountered like roller support, hinge support, pin support, fix, etc. In week 2, we moved on to trusses, how real life trusses are idealized using axial force members or two force members, and the stability of trusses and solving the member forces in a truss using two methods, the method of joints and the method of sections. And in week 3, we tried looking at the other kind of response of a structure. That is there are two kinds of responses of a structure: the forced response and the displacement response. We started with the principle of virtual work and then looked at the unit load method to determine displacement in trusses. In week 4, uh, the same thing was done for beams using elastic curve equation method, moment area method, and there is another method called the conjugate beam method that was covered in week 5. And now we are here in week 6, where we will look at influence line diagrams or ILDs, which will cover some topics like basic instruction about how to draw an ILD, about the Muller Breslau principle, and how to find absolute maximum bending moment and shear force under combinations of loads like a single point load, a series of point loads, or uniformly distributed load greater or lesser than the span. Yeah, so influence line diagram, so how to draw them, and then Muller Breslau's principle about how to draw an influence line diagram qualitatively, and how to find out absolute maximum bending moment and shear force under various types of loading that we would encounter in a structure, in a beam in specific here, like a point load, a series of point loads, or a uniformly distributed loads greater than or lesser than the span. We will find series of point loads. For example, when a truck moves across a bridge, it has suppose four sets of wheels in the transverse in this plane. So it will be a series of 4 point loads. Or for a car, it will be a series of 2 point loads. A uniformly distributed load, for example, a tractor with a continuous base, a uniformly distributed load can move across the bridge. We when we talk about influence line diagrams, we usually visualize a bridge, but that doesn't mean a bridge is the only. I mean, the ILD is used only for bridges. We also use it for beams. We use it for any beam, like a beam used in any kind of structure. So there are two major types of loads. Firstly, dead loads and live loads. Dead load includes the self weight of structure. For example, the weight of the concrete, the weight of the steel, the flooring. For example, the marble that we have put, the flooring and the self weight of structure that remains constant and stationary. It does not move, it does not change across the lifetime of the structure. So hence the variation of the bending moment, shear force, deflection, or reaction forces, or any kind of response of the structure due to the dead loads also do not change across the lifetime of a structure. So along all sections, though these responses remain constant. But there is another kind of load, live load, that For example, in a building, once a building is constructed, we put furniture. We and there are people inside the buildings, inside the building, or any kind of load we place. We place a bucket on the. I mean, a bucket is a very lightweight thing, but a bucket on the floor, furniture, any kind of thing is a live load. That apart from the self weight and floating, that is constant. Anything that comes is a live load. In a bridge, for example, it's easier to visualize that wheel loads, passenger weights in bridges, all that are live loads. So they, of course, their position and magnitude vary with time. So we need, so basically the response of the structure for the live loads does not remain constant. So yes, yes. So we need some kind of methodology to find out how the response will vary as the magnitude and position of the live load varies. For example, like it will be much easier than calculating the bending moment and shear force diagrams every time. Of course, if a combination of live load is given to you along the section of a beam, you can find out the bending moment and shear force diagram using the methods we have learned earlier. But rather than taking each specific live load combination and calculating the bending moment and shear force diagram again and again, the influence line diagram basically provides a simpler method that where you basically, this is what we do here in an ILD. It is a diagram that represents the variation of stress functions. Now, the stress function term is new, but it is basically just, it can represent any kind of response of the structure like the bending moment, the shear force, the slope or deflection at a fixed section when a unit concentrated load moves from one end to the other end. So, there are a lot of clauses in this definition. So what do we have for, so when we draw an influence line diagram, what do we have to specify? We have the beam, we have the boundary conditions, that is fixed. Now we take one section, like along the beam, maybe we are taking the midpoint, maybe we are taking one point inside the beam, but that is the only section we are going to look at right now. In the difference between influence line diagram and bending moment and shear force diagram is that in bending moment and shear force diagram, we estimate or we study the variation of bending moment or shear force along the section of the beam. So as we draw the diagram along the line of the beam, the section of the beam is changing. But here in influence line diagram, we fix one section. We are suppose only looking at the midpoint, but the force varies. The position of the force varies. In bending moment and shear force diagram, the pattern of the force is fixed, and we draw the diagram along the variation of the bending moment along the beam. And here we fix the section while we move a concentrated load from one end to the other. Like the load is at the leftmost point, then we move it towards right till it reaches the other point, and that is how the influence and diagram varies. An example will make it clear. Once we have the idea of particular stress function at a particular section, we would use the principle of linear superposition to calculate total effect due to a combination of loads. Now, this we will go into details later, but just for example, suppose I have the influence line diagram of the bending moment at the midpoint of a simply supported beam at the midpoint. We have the influence line diagram that is due to a unit load, a 1 kilonewton load moving from one end to the other. Now, suppose we suppose now I want to find out the bending moment at the midpoint for a certain pattern of loading. So for that actual pattern of loading that we have, it can be divided into a number of unit loads, like a number of unit loads into some factor that adding up will give us the total force pattern, and that is where the principle of linear superposition comes in, that the response of a structure is basically, it can just be added up. Like if I have 2 point loads on a structure, I can take the response due to 1 point load, then I can take the response due to the second point load, and we can just add the responses. We do not have to consider both of them at the same time. So of course, examples will make this clear. First, we look at how to draw the influence line diagram of a simply supported beam. Yes. So here, for the simply supported beam, like it has two hinge or roller supports at A and B, and we are looking for the ILD for the reaction RA. So that is what basically what do we need to say what do we need for to specify for an ILD? We need the we need the length of the beam, we need the support conditions, and we need the position where we have to find the like the section we are looking at and the response. Now this reaction Ra is self-explanatory, like Ra is only present at this point. So the response we are looking at is reaction, and the section we are looking at is this A point. So what we will do is we will take a unit load 1 kilonewton at a distance x from this support. You can take from the other support as well. Now, to find the ILD for RA, we will consider moment about B. When you consider moment about so sigma MB equal to 0, what we will get RA into L is in the clockwise direction minus 1 into L minus X, right? Because this is X, so this distance is L minus X is 0. So we get RA is L minus X by L. This is the basically the variation of the influence line of RA with X. This will of course always be a function of X, and you can see this is a linear function. So we just need to find it out at 2 points, and we can join them by a straight line. At x equal to 0, RA is 1. At x equal to L, RA is 0. And you can also visualize it, like for example, when x equal to 0, the unit load is at this point. So if the 1 kilonewton was applied at the left support, then Ra will be 1 and Rb will be 0. Like then the entire load will be taken by this support alone. And so that is why when the x is 0, that is when the unit load is applied at this point of support, then the Ra will be 1. And when this will be applied at this point, like the at the RB at the hinge support at B, reaction A will be 0. It will not take any reaction. The entire reaction will be given by B alone. So the influence and diagram for RA will look like this. It will be 1 at x equal to 0. It will be 0 at x equal to L. And we will join it by a straight line. For RB, it will of course be the opposite. We find out that using a similar method, we will take the moment about A. When you see, it doesn't matter whether you're taking x from this end or that end. It's just that you will put 1 kilonewton, even kilonewton doesn't matter. A load of magnitude 1 at any point at distance x from this side or that side, and you will just find out the moment and equate it to 0, of course. So sigma ma equal to 0. From that we get at RB equal to x by L. So again we put at x equal to 0, RB is 0, and at x equal to L, RB is 1. So the diagram will look like this. At when the there is this means that when the point load is applied at B, the entire reaction is taken by B, so RB is 1. And when it is applied at RA, this will be 0. And you can see that adding up this RA and RB, you will get a constant diagram of magnitude 1, which is how it should be, because the equation of equilibrium in the y direction is RA plus RB equal to 1. So this diagram plus this diagram has to be 1 uniformly. Next, we look at ILD for the shear force at XX. Like at this point, this is a section I've taken XX. This is at a distance A from this. Like XX is not a random section. It as I said before, we have to for the ILD we need to fix two things. We need to fix the position or the section, and we need to fix the kind of response we are looking for. So here we are looking at the shear force response at this point, at this particular point of the beam. So here also we will follow the same approach. We will put a unit load in this portion AC and then in CB, because there is a break here. So for portion AC, when the unit load is within AC, that is x less than A, here you can see that SX, using just from coming from the left side, you can simply see that SX is RA minus 1. Just the way we worked during bending moment diagrams or shear force diagrams, we come from one side. We come from this side and we find that X is RA minus 1. And when this is what it is, Sx is Ra minus 1, and Ra we already found out is L minus X by L. So Sc is minus X by L. And when this it is in portion CB, like at this portion, if you come from this side, if you come from the right from the left side, you can see that SC is simply equal to RA, because when this load is in this position, if you come from the left side, you only encounter RA in the upward direction, nothing else. So it is L minus X by L. And here again, see, this this SC is minus x by L, this SC is L minus x by L. These are both linear variations. So again, we just need to find out its value at two extreme points and just join them by straight lines. So at x equal to 0, we find that SC is 0. At x equal to A, SC is this. And so the way we draw it, it looks like this. From A to C, it goes in the negative zone because it was minus x by L. And then it has a jump. And this jump magnitude is equal to 1 because when the point load is at the section x6, there will be a jump in the shear force diagram. It is not a shear force diagram, it's an influence line diagram, but that is how we can interpret it. And it will then go down to 0 again at RB. And another kind of response we get is moment response. So this here we look at the moment response at section XX. The bending moment diagram at section XX at this point. And again, we will put 1 kilonewton load first in position AC, then in position CB. So when the unit load is within AC, we find about like we take a moment equilibrium that MC is RA into about this point. We are taking the moment about this point from this side. So we will get RA into A minus 1 into A minus X. That is what is done here. So we get an equation of MC as in terms of X as X into L minus A by L. And then this is a linear profile. So we can find out two extreme points and find its values. And in position CB, again, we take the moment of when the force is here. When the force is here, we again take the moment about C. So we get RA into A simply because we are coming from this point. We just take RA into A because this load is now here. It doesn't, if you come from the left side, it does not have any effect anymore. Now, of course, we could also come from the right side. I've always told you that there is no difference. I mean, it's up to you which side you are coming from. If you come from this side, then for when the load is in this zone, in AC, the moment will simply be RB into L minus A. And we also know the expression of RB. So you will end up with the same expressions either way. And the moment diagram will look like this. It linearly goes up to this value and the linear decreases to 0. And just physically you can see that when the load is at this point, when the load is applied at a reaction point, there is no shear force or bending moment in the entire structure because it's like no force is applied at all. Because if 1 kilonewton is applied here and 1 kilonewton reaction is given, they will cancel each other out. So at the extreme points, for both the ILD of SF and BM, at A and B, the values are 0. So that is not surprising. That is how it should be. The next example we look at is a cantilever beam. As is a simple cantilever beam with. So again we look at reaction. What kind of reactions can it have? It can have two kinds of reactions. Like at A there will be a reaction. At A there will be a moment, and we can find a general. We will take a section XX here at distance A from this point, and we will look at the ILD of shear force and bending moment. And here when we are taking the ILD for RA, we will consider the summation of forces in the vertical direction. So it will be RA will always be 1. Whether the 1 kilonewton is here or here, the entire reaction has to be taken by this A point. So RA will be a constant 1 like this because there's only one upward reaction. Then when you look at the moment for A, ILD for moment at A, the moment, if you look at MA, you will see that this distance is X. Okay, we are varying it from this side. So the reaction at A will be L minus X into 1. And this will be minus because it's a hogging moment. We know that hogging moment or this direction moment is taken negative. As since we are see, this is not a bending moment diagram, but we are drawing the influence line diagram of the moment, right? So we have to follow the sign convention that we use for bending moments. So hogging moment here is still negative, and this is minus L minus X. So it looks something like this. It is a straight line that varies from 0 to L because even physically you can see when the load is applied at the tip at this B, what will be the moment at the reaction? It will be L into 1. So at this point, the moment reaction is L. And if this point load is applied at this point, there will be no moment reaction because the reaction is here at the point, very point the load is applied. So it decreases to 0 here or increases, and because the sign is negative. And here we look at the shear force and bending moment influence line diagrams. for this particular section. Again, the section has to be fixed. For reactions, we need not mention the section separately because the reaction has to be at A. There can't be any other reaction in the, I mean, there cannot be a reaction at C or something. So for reactions, we do not need to specify the section we are finding it at. But for shear force at bending moment, it is mandatory we define this section. This section that is at distance A from this point. So we will put the load first in this zone BC and then we will put it in CA, and we will just apply the equilibrium equation. Like we will come from the left side when the load is here. We can see that the shear force at this point will be 1. Why is it positive? Because when we come from the right side, downward shear is positive. So in this position, force is 1. And when look at this position CA, when the load is applied here, if you come to this section from the right side, you can encounter no load at all. No load, no reaction. So in B, when the load is in AC zone, the shear force diagram will be uniformly 0. So this is how it will look like. In this zone, it is 0. And in this zone, it is plus 1. And similarly for moment, when the force is applied in the zone CB, there is a moment of 1 into A minus x, and that is negative because it's a hogging moment. And when the force is applied in this zone, if you again come from the right side, there is no force, hence there is no moment. So in the position AC, the ILD of the bending moment will be 0, and here it will be minus A because this is the expression. MC is minus x minus A. So at x equal to A, this will be 0, and at x equal to 0, it will be A. This is x equal to 0 basically. This is how the influence and diagram of the bending moment at that section C will look like. You have to define the section. Don't forget that you cannot find out the bending moment diagram. You cannot find the influence and diagram of bending moment of the entire beam. You can only find out bending influence and diagram of the bending moment at a particular section in the beam. So this was another example, the cantilever beam. Then this is known as a simply supported beam with an overhang. One second. Yeah. This is known as an overhang. This is basically a simply supported beam that has an extension here. And there can also be a cantilever with overhang. Like if there can't be a cantilever with an overhang, there can be a prop. You know what a prop cantilever is? A prop cantilever is when this is a fixed support, and if A B up to if this wasn't there, it would be just be a cantilever. If there is just one fixed support at one end, then if there is a roller support at the very tip of the cantilever, it would be called a propped cantilever. Like if this BC portion wasn't there and the A was a fixed support, then it would be a propped cantilever. And if there is any extension, then it will just be called simply supported with overhang or cantilever beam with overhang. So that is what this terminology means. Here we are finding out first the influence and diagram for RA. So what will we do? We will put a load 1 kilonewton at in this zone and then in this zone. Of course, then there is a different, when there is something is changing at a section, you have to take the two zones separately. A, B and BC you have to take separately. So in portion AB, when this load is applied, look at RA coming, we will take the moment about B. We will take the moment about B because if you take the moment about B, the RB term will cancel out, right? So that is why we are doing this. RA into this distance, this is X, this is L. So, and minus 1 into L minus X. So this is the expression. RA into L minus 1 into L minus X is 0. Because, moment equilibrium, about B, we have to equate the total moment to be 0. So RA is L minus X by L. This is the same as how what we obtain for the simply supported beam in this zone. And for this zone, when we put the load in this zone, we will take the moment about, we will again take the moment about B. And here we will find that here, when we apply the force here, we will find that RA into L plus 1. This is 1. This will be again, this is plus because see, about we are taking a moment about this point. So this RA is giving a moment in the clockwise sense, and this 1 kilonewton is also giving a moment in the clockwise sense when it is on the right side of B. So it is RA into L plus 1 into Z minus A. This overhang length is Z. And we get this minus Z by L expression. And when we draw this, we get an unbroken straight line. In influence line diagrams are actually always continuous of a reaction force, but don't take that for granted. You draw this and you will see that it comes in a straight line. And we can find out the influence line diagram of RB similarly in the exact same way. We will first put the load here. Then we will take the moment about A, because if we take the moment about A and equate it to 0, on RB will be the only unknown term in the expression. So we are taking MA equal to 0. So here minus RB into L about this point. So RB is taking it as minus because it is in the anti-clockwise sense, plus 1 into X, because this gives a moment in the clockwise sense. So we get RB equal to X by L. And in this other position, similarly, we take sigma about moment as, sigma of moment about A to be 0, and we find this L plus Z by L, uh, L plus Z minus X by L. And see, these at X equal to 0 and at X equal to Z, these we are doing to draw, because we know this is a linear variation. And when we know that something varies linearly, we can just find its value at points and join them. So here we see that it is again a straight line of this kind. And here also, RA and RB, if you add the two influence line diagrams, RA and RB, you will find that it will be a uniform one, because that is the governing equation of this like of a beam, of this beam. If there is a 1 kilonewton, wherever we put it, at whichever the 1 kilonewton may be anywhere, but RA plus RB has to be 1, because that we need to satisfy the equilibrium in the y direction. We look at some other parameters, like we take a section D, section XS, that is at distance A from this point A. So we have to put here we have to put the 1 kilonewton in three positions. Like we are taking this section and there is a reaction here. So we have to first consider position AD, this portion AD, then DB, and then BC. So because wherever you encounter some sort of a change, you have to consider it separately. When we put the 1 kilonewton here, we get this expression SD is minus X by L. How are we getting it? We are just taking this, we will just take the shear force about this point, about at this section. We are coming from the left side. So RA is upwards and 1 is downwards. So SD is RA minus 1. And RA expression we have already found out. You have to substitute that, of course. Then when it is in position DB, when the 1 kilonewton is here, if we come from the left side, we will just encounter one reaction, RA. So this SD when X is RA, and nothing changes when the force is at this in this zone in BC. Again, if we come from the left side, we will get RA only. So this RA, but see, the expression of RA changes when the unit load moves from DB to BC. So see, here RA has been written as L minus X by L, and here RA has been written as Z minus X by L. This is why when you have to draw the influence line diagram of any shear force or bending moment at any section, you first have to find out the influence line diagram of the reactions, like the expression of the reactions, because the reactions will occur in the expression of whichever you encounter further. So RA, here you can see that RA, when the force was in this, when it was in AB, the expression was L minus X by L. So when it is in DB, this will be the expression, and when it is in BC, this will be the expression. So this varies, like uh, this is so though SD is RA, whether you are in this zone or this zone, the expression of RA itself varies. So you have to put the RA accordingly, and if you draw them, they are also linear. You can see the linear in X, so it will look like this. There is a jump of unit 1 magnitude again here. That this is a thumb rule you can remember whenever you are finding the influence line diagram of shear force at any section. Since you are applying a unit load, there has to be a jump of 1 kilonewton at that point, at the section that you are considering, which is D here. And again, the bending moment diagram at D. Just keep noting that whenever we are talking about influencer diagrams, we are looking at two things. We have to fix two things, like the moment that we are, whether we are considering the moment or the shear force or the reaction, and the section at which we are interested. Here we are interested in section D, and we are interested in the bending moment. Similarly, we have to take this 1 kilonewton in this zone AD, then in DB, and then in BC, and we get the expressions. And when we plot it, here again, there will always be a function of RA, and the RA you have to put correspondingly, like in DB, the RA that we found out for this zone, the RA that we found out for this zone, and it looks like this. Okay, so these are the basic tips of calculating bending moment of any kind of influence line diagrams. This is another section that we are considering, Like if suppose we want the shear force or bending moment ILD is at this section, so they will change. So here again we have to consider three portions A, B, B, E, and EC. You will see that whether it is in AB or BE, if you come from the right side, you will see that there is no load encountered. So no shear force encountered, no moment encountered. So the shear force, this ILD for shear force or bending moment will be zero up to this point E, and up from here, when the load is here, if you come from the right side, like if you take the shear force at E, you will get it as +1 because though the load is downwards, when we come from the right side, downward shear is positive. And for the moment as well, you can see if there's a 1 kilonewton meter applied here at a distance x, this will be 1 into b minus x. So this is how this will look like. Then we look at the Muller Breslau principle, which is this was I mean that was how we calculated the influence line diagrams quantitatively. When you can find out any kind of graph or diagrams either qualitatively or quantitatively. Qualitatively is when you know the shape, when you know the nature of the graph. For example, if I give you an equation x, if I give you the equation of a circle like x square minus a square is 1, then you can or an ellipse. Suppose x square by a square plus y square by b square is 1. Then you know that the ellipse will look, you know how the kind the ellipse will look like. But unless you know the values of a and b, you do not actually know that what you don't know the values of that. So that is what a qualitative analysis is known as. So this was a method that we followed the principles of equilibrium, we followed the principles of bending moment and shear force and the sign conventions to find out the exact values. These are the exact values. So the Muller-Breslau principle is just help us to get an idea of how the influence and diagram will look like. Its statement is the ILD of any stress function in a structure is represented by its deflected shape obtained by removing the restraint obtained offered by that stress function and introducing a directly generalized unit displacement in the positive direction of that stress function. These statements always sound confusing. What are the clauses we are finding? First, we have to choose a stress function. What are these stress functions? They can be bending moment, shear force, or reactions, as we saw. It is represented by its deflected shape. We remove the restraint offered by the stress function. For example, if suppose, for example, we want to find out the influence line diagram of reaction A of a simply supported beam. Remove the reaction, remove the RA, and then we have to introduce a unit displacement in the positive direction of that stress function. So remove A, imagine there is no support at A, there is still a support at B, and you displace that A point in the positive direction, like upward, you give it a displacement of 1. Then what will it look like? You have pulled the point A up by one unit and the B is still fixed. At B there can be no displacement. So if this was how the simple solid beam was. You removed A first, then you gave it a unit displacement, it will look like this. You can just visualize it. It will look like this. And this is how the influence line diagram of RA look like in a simply supported beam. This is exactly how it looked like. Like you remove A, you displace it by a unit displacement in the upward direction, it will look like this. But this one value, this you do not know. I mean, we are given a unit displacement, but we do not know what the reaction value is. So it will be like this will be some constant displaced. This constant will be unknown, but the nature of the diagram will be like this. So this is how and the Muller-Breslau principle basically says. This is an example that will help. Using the Muller-Breslau principle, draw the ILD for reaction B and find the ordinate of ILD at E and F. You have to this ordinate of ILD you have to find in a separate way. So for the ILD of RB, we first remove the restraint. That means we remove RB. Imagine RB is not there, but RA is still there. You just have to remove the reaction we are talking about and we provide a unit deflection in this direction. Like in the upward direction, we pull it by 1. If we pull this by 1, displacement, this will rise up and this part will go down because at this point A, there cannot be any displacement. A is still here. So here we remove B and we pull it up. This point remains same, so it will look like this. At A, the deflection will be 0. This is the deflected shape of the beam. So at A, the deflection will be 0. This part will go down and this part will go up. This is the qualitative analysis of the part. And by property of similarity of triangles, we know that this B dash by F dash is this length by this length. So these lengths have been given. So if this B dash is 1, we have to say that, and 1 second. Okay, and see, this one is here because this one we know not because we have given a unit displacement. This one we have to find out using our judgment. Like we know that when the force is applied at B, which is the ordinate, which will be the ordinate of the ILD at this point, the reaction at B will be 1. So we know that this ordinate will be 1. We know that. And this shape we have found out. So since it's a linear profile, using geometry, we can find out these ordinates. Like at BB dash, if it's 1, at FF dash, it will be 7 by 4. At EE dash, it will be zero point 0.5 because this is 2 and this is 4. Like, you know that EE dash by BB dash is this length by this length. So, this is how we can find out the ordinates because this is a once you know the nature is linear and you know the value at one point, you can find out the values at other points. It is not mandatory to use the Muller Breslau principles. If it seems confusing, you can just go at it from the using the first principles. Like we already studied this same beam, like this cantilever with we studied of simply supported with one overhang, but we could have done it with two overhangs as well. And this is the nature we would have gotten anywhere. But suppose the ordinates are not asked, like suppose this ordinate of ILD at ENF is not asked, then and you are given a kind of a complicated beam, you can just remove the reaction, pull it up, and you can just understand the nature of the beam. So in MCQ questions, this principle might help, but in qualitative questions, I would suggest that go through the whole method that we are going. Now move on to the now that we know how to draw the ILDs, we look at. We know how to draw the ILD of a given beam with given support reactions of a particular kind of response at a particular section. Now we are interested in how we will apply it. Like we said, we needed to find out the response of a structure under live loads that whose position and magnitude changes. So that is what we are going to look at now. The ILD is used to study the effect of a moving load on a structure. It is used to find the position of live load, which will produce maximum value of a particular stress function. This is important. Like there are two kinds of problems we can find. Like firstly, it can happen that we know the exact position and magnitude of a live load, and we want to find out the bending moment or shear force at a particular section. There's another kind of problem that we know that a live load, like we know the pattern. Suppose there is a truck, we know a truck with four sets of wheels, and we know that there is 2 kilonewton, 4 kilonewton, 4 kilonewton, 2 kilonewton. That kind of a loading system we have, the truck can move from the left side to the right side, and we want to find out which position there will be a maximum value of bending moment at the midpoint. That is how we have to design a structure. Like when we are designing a structure, we have to know the absolute maximum responses. We cannot just assume that the truck will always be in the midpoint or the truck will always be at the corner. We have to consider that the truck or any load can be in all positions, and at which position it will produce the maximum moment or the maximum shear force. According to that, we have to design the bridge and to calculate the total value of particular stress function due to multiple load system. Like if there is one truck here, one truck there, a series of people walking, so a series of point loads. So we can uh, using the principle of linear superposition, we can find out the total response using the ILD once we just have the ILD. So we have to this is how the application influence and diagram. For example, you are given this. Find the shear force and bending moment at the section shown for this loaded beam C at this section. Now, of course, there you do not have to use an ILD for this. You can just find out the reactions. You can just come from like work from this left side and see that this will be RA minus 50 minus this force. So that is there's always one option. But using the ILD, you can. But if I change something, if I change this position a little bit, you have to you have to recalculate the entire thing. But the ILD, for the ILD, what was fixed? For the ILD, bending moment and or shear force, and this section is fixed. So you can apply it anywhere this loading is placed, you can find it. Now, first we have found out the influence diagram for this. Okay, then which we found out earlier. This is basically just a simply supported beam. For a simply supported beam, for a shear force at a section like this, we already found out the this ILD. See. This is simply supported beam. Now, see this, it can have any kind of loading. It does not, of course, it does not always have to be 1 kilonewton loading. And once you have drawn the ILD, forget about the 1 kilonewton. We know that at a section A from one end, the ILD of shear force diagram looks like this. We know that this ordinate will be L minus A by L, and this will be minus A by L. So now, here you draw the influence line diagram. You just draw the influence line diagram. You substitute the value of A as 3 and the value of L as 7, right? So this will be 4 by 7 and this is 3 by 7. And you can see that just adding this magnitude, you get 1, which I said that there will be a jump of 1 kilonewton in the ILD. You have just drawn the ILD so far. Then you draw the ILD below the actual loading. Okay, you don't know the actual loading initially. First, just draw the ILD. Forget about the actual loading. Now you come to the position of the loads. Like this 50 kilonewton is applied at 1 meter from here. So suppose this point is called C. So now we need the ordinate of the influence line diagram at C. We can just find it using similarity of triangles. This is 3 by 7 at 3 meters. So at 1 meter, it will be 1 by 7. This is 1 by 7. So for the shear force at x6, you just go on adding them algebraically. See, this is minus 50 and this is minus 1 by 7. So you will get, sorry, if this 50 is taken as positive because we are considering that. So 50 into minus 1 by 7 plus this loading is 60 kilonewton total. So 60 kilonewton, 60 kilonewton meter. So see what you have to do. This is the portion we are concerned about. Like when we are coming, no, I'm sorry, where you have to consider the entire portion. Like this entire zone has some kind of distribution of the influence line diagram, like this a negative part and this is a positive part. So you have to find out the total area of this. Okay, the total area of this influence line diagram and multiply it with the magnitude. Here what we did, when there is a point load, you simply have to find out the ordinate and multiply it with the magnitude of the point load. But when there is a uniformly distributed load, you have to find out the area and you have to multiply. So 60 into this is a parallelogram. So this is half into yd plus y this x into 1 because this is 1 meter. Then yd and this yx we already know 3 by 7 and yd will be 2 by 7. I mean minus, you have to take it with sign. So 60 into half into this into 1. And for this zone, this is positive. Here the ordinates are positive. So 4 by 7 plus 2 by 7 into half into 2 because this length is 2. This is basically just a parallelogram. Like when you're finding the area, you can just use the properties of geometry, the kind of things you know. So this is so that for the point load, it is the magnitude of the point load into the ordinate, and for distributed load, we use the magnitude of the distributed load into the area. So this is how we get we using. We have don't forget the signs because these cancel each other out. Like this is a negative one, this is a negative one, and this zone has a positive influence. So they will cancel each other out, and we will get like this 160 by 7 kilonewton. And similarly, we want the bending moment at this zone. So we go back to our ILD that we found this at a section A from this end, we know that the bending moment diagram looks like this. A into L minus A by L. And here A is 3 and L is 7, right? So see, A into L minus A by L is 212 by 7. So this point is 212 by 7. And since these are straight lines, at 50 kilonewton, you can find this YC ordinate. It's found as 4 by 7. And we need the ordinates at this point and at this point as well. Because again, we need this area. So for the point load, it is 50 into 4 by 7, which is positive. Here all the ordinates are positive. Plus 60 into this area of this parallelogram into area of this plus area of this parallelogram. So half into ye plus yx into 1 and this. So finally we get this as the bending moment. Here everything is positive, so nothing cancels out. So here you see that basically even if I had removed this, like extended this uniform distributed load by some zone, like some, we suppose I put it up to the end, like I put from D to B, I put a uniform distributed load, or I change the magnitude. You just have, so long as you have the ILD, you only have to apply some geometrical operations, like take the area under the uniform distributed load, or just take the ordinate at the point load. I can add any number of point loads, any distribution of UDLs, and it will be, and you just use the ILD. After once you have the ILD, you can apply these simple principles to get the bending moment or shear force, no matter what the loading arrangement is. However, if you use shear force bending moment concepts from equilibrium, the moment I apply this force, the reactions will change. So you have to treat the problem as a new problem as the loading changes. But in ILD, the problem doesn't change as the load changes because the ILD remains constant. You just have to put the loads and you have to calculate the corresponding ordinates of the areas. This is another example. See, two wheel loads, 50 kilonewton and 150 kilonewton, spaced at 2 meter, move on this girder is also a name for a steel beam. So this is a beam, simply supported beam of 12 meter. Find the values of maximum positive and negative shear force at a section 3 meter from the left end. Any wheel load can lead the other. That means that 150 can be on this side, 50 can be on that side. What does two wheel load mean? For example, a car. In a car, there are two sets of wheels. Suppose the front wheel is giving 50 kilonewton and the back wheel is giving 150 kilonewton. So the car can move and the spacing is of course fixed. The spacing between the loads is fixed. It can move like this, like the 50 is on the right side, the 150 is on the left side. It can move across the beam and then move like this. Then it can also move, suppose it is moving on the other lane from this side. So the 50 is on the left and the 150 is on the right. It can move. And I don't know the position that will cause the maximum responses. I am interested in this section. Why am I interested in this section? Because let's suppose I want to design this section. I want to find out to design the depth of the beam or the amount of steel I have to give in that point. I need the maximum bending moment and the maximum shear force that can be generated at that point. I know the kind of loading, but I don't know where the loading will be. So see, for max, firstly you have the ILD at C. You have the influence and diagram of the shear force. It will look like this. Here A is 3 meter and L is 12 meter. So the ILD will look like this. This is 3 by 12. It has a jump, and from 9 by 12 it reduces to 1. And now I need maximum positive shear force at C. Maximum, you see, if now you see that this ordinate is the maximum. So if you put the 150 kilonewton at this point, you can find out you will find the worst positive shear force. So we will put the 150 kilonewton just like to the right of C at this point, and the 50 kilonewton on this side. Why are we putting the 50 kilonewton on this side? Because if you put on that side, this will cancel out. Like if the 50 kilonewton has a negative ordinate, it will be 150 into 9 by 12 minus some value. On the other hand, if you put it like this, that 150 is here and the 50 is here, it will give the worst positive moment. And this you have to understand logically. Okay, you cannot calculate it by putting it everywhere. From biologically, if you have a series of wheel loads, you put the maximum wheel here, you put the heaviest wheel here, and the second heavy, like the lesser heavy wheel on the other side, where it is also positive. Since we are now considered about the maximum concerned about the maximum positive shear force, you put 150 here and 50 here, and this is 2 meter, so if this ordinate is 9 by 12, using similarity of triangles, you know that this ordinate is 7 by 12. So it will be 150 into 9 by 12 plus 50 into 7 by 12, and this is what we get, the maximum positive shear force at C. Now, if we want the maximum negative shear force at C, what will we do? We will again put the 150 here only, just to the left of C, so that we get to utilize this maximum negative coordinate. So we put 150 here and we put the 50 here because this is also a negative ordinate. So they will add up in the negative direction. So 150 into minus 3 by 12 plus 50 into minus 1 by 12. And this magnitude is the maximum negative shear force. This we are basically doing logically. Like we have to put the heaviest one on the biggest ordinate and the lesser heavy one on the ordinate which has the same sign. This here we are trying to find out like a similar problem. We are trying to find out the maximum bending moment at a section. So two wheel loads, 120 and 80 kilonewton, are spaced 2 meter apart, is moving on the span of this girder. Find the maximum bending moment at section 6 meters on the left end. This First you draw the influence line diagram. How do you draw this? This is a simply supported beam with A equal, like A, and we have taken a section C here with A is 6 meter and L is 16 meter. So here we know this for simply supported beam. The moment diagram of the influence line diagram of moment for this C point looks like this: A L into L minus A by L. So this we find out to 15 by 4. A into L minus A by L is 15 by 4. The maximum bending moment at C will occur when the lighter wheel load leads and the heavier load is just at the section C. Why do they say this? Because Firstly, the heavier load you always have to put on the biggest ordinate. This is the largest point, and I mean the biggest ordinate. So put the 150 kilonewton here. Now 120. Now the 80 kilonewton can either be placed here, like 2 meter on this side, or 2 meter on this side. Now why are we placing it on this side? Because see, this is 6 meter. This goes up to 15.4 in 6 meter, and this goes to 15.4 in 10 meters. So you can understand using the similarity of triangles that the ordinate at 2 meter from this side will be larger than the ordinate at 2 meters from this side, because this is a smaller slope. It will fall off slower, and this is falling off faster. So if you have problem visualizing it, you can just calculate the two. If you calculate the ordinate here, you can see it will be less than 3. The Because this falls to 0 from 15.4 in 10 meters. So the slope this is a gentler slope, and this is a steeper slope. So obviously, if you go 2 meters on the gentler slope or 2 meters on the steeper slope, you will end up at the higher ordinate when the slope is gentle. So here we are placing the 80 kilonewton. These are some kind of thumb rules. Like there are only a set number of kinds of questions you will encounter in the exam. So if you practice a bunch of 10 questions, you will eventually understand these small techniques of all the kinds of questions. But they also follow by logic, of course. So the maximum bending moment at C will be 120 into 15 by 4 plus 80 into 3. This is the maximum bending moment. This another question we're looking at is that two wheel loads. These are placed at a fixed distance 2 meter apart. The load crosses simply supported beam AB of 10 meter span. Draw the influencer diagram for the bending moment at shear force at section C, which we have already done. In terms of A, we know that, and find the maximum bending moment and shear force at that point. So this is the same question as the previous one basically. We draw the bending moment influence and diagram. A in this maximum ordinate is A into L minus A by L. And we will put the 16 to find the maximum bending moment. We will put the 16 kilonewton at here and the 8 kilonewton on this side, because this is 6 meter. This is the gentler falling off. So this is how we place it. 16 here, 8 here, and we just add them like 16 into 2.4 plus 8 into 1.6. And for the shear force, what do? We again, here we don't see, here they have said that find the maximum shear force at that point. If they said the maximum shear force at that point, don't assume that you have to find the maximum positive shear force, because positive and negative here is only related to sign, but in magnitude, you have to take the maximum magnitude. So if you're asked to find out the maximum shear force at any point, find out the maximum positive shear force, find out the maximum negative shear force, and report whichever magnitude is higher. So for maximum negative shear force, here, see, here basically, they have not said any wheel can lead the other. If they have drawn it like this, it is like the 8 kilonewton has to be on the left side, basically. So you don't have a choice. So if you had to actually find out the maximum negative shear force when the wheels can be oriented in any direction, you would have put the 16 here and the 8 here. But here you don't have a choice. So put the 8 on this point at the maximum point and put the 16 here, because if you put the 16 here, the 8 will go into the positive zone, and that you won't get the maximum negative shear force. So 8 is just to the left of C. Why are we saying just to the left of C? That means we are taking the negative ordinate. So 8 into minus 1.4 plus 16 into minus 1.2 will give the maximum negative shear. For the maximum positive shear, you will put 16 just to the right of C. So you get the positive ordinate, and 8 accordingly, and you get 12.8. So this is the maximum shear force at C, because this magnitude was 6.4, this magnitude is 12.8. And we look at another example where this is not they're not simply supported beams, this is simply supported beam with two overhangs. So we have two wheel loads, 200 kilonewton and 80 kilonewtons, placed 8 meter apart. Yeah. And they are moving. You have drawn like this, so you do not assume that any wheel can lead the other. You have to take this arrangement that a 200 kilonewton is on the left and 80 is on the right. You take the ILD for bending moment at C. You draw this. If you draw, you will see that it looks like this, and by the time you have a bit of experience, you will know that this will look like this. Like we drew bending moment diagram for a simply supported beam with one overhang. See, this is our simply supported beam with one overhang. And if you look at the bending moment this at this section, this looks like this. it rises, it falls, and then it goes in a negative using the same slope and ends up here. So, and if there's another overhang, it will be a similar thing like this. You have to extend this. So you have to draw this part like L minus A by L will remain constant in the simply supported beam, and you just have to extend these parts to the ends. So this is what we actually get here. This point, this is with this YC is A into L minus A by L. What is A? A is 3 meter and L is 7 meter. Don't take the whole length. When you are using when you are finding out when this influence line diagram of a beam with overhang, this L will still remain this zone of the length of the simply supported zone. So this is how the diagram will look like. Here it is. See, this will fall off to the same. If you extend this, you can see using this ordinate 1.714. You don't know yet, but if you use similarity of triangles, you will see that these are what you are getting because see this is 1.74. This is 3 meter, this is 3 meter. And if you extend by the same slope, this will also be the same 1.714. But this I am extending from the ILD of a simply supported beam, a simply supported beam with one overhang, then a simply supported beam with two overhangs. But you do not need to use this if it isn't obvious to you right now. You can just find out the influence line diagram using the method we first studied. What would we have done? We would place a 1 kilonewton load at DA, then we'll put at AC, then at CB, then at BE. In four zones we will find out, and in four zones we will get these straight lines and draw them. We will end up with the same ILD, and you want the maximum positive bending moment at C. So it will occur when this big load is when this largest load is at the maximum top point, and the 80 is somewhere here, and this is 8 meter. So see, the 8 meter will basically it will cross over to this zone. If you put here, the other will be at absolutely at this point. So the maximum positive bending moment at C is this, and see, suppose that said any wheel can lead the other. Suppose you could have put the 200 here and the 80 this side, then what would you have done? You would put the 200 here, and if you put the 80 at this point, then we get YC into 200 minus this value. But if the wheel was oriented other side, like if the 200 was leading, then the 80 kilometer would be out of the span of the bridge because this is 6 meter and the total distance between the two loads is 8 meter. But that you can also consider because that is a practical case. Like when the car is entering from one side, one wheel might not have entered the bridge yet. And then you would have then see what would have happened if the 80 kilometer was outside the span of the bridge, then the maximum bending moment would be 200 into this ordinate. Then it would actually be just this part, and that would be the maximum bending moment, not this, because this also has a negative component from this end. So be careful, like just think about all the different orientations that there can be, and you can figure out, like you can reason out logically which would be the maximum one. If you have doubts, you can try a few combinations, you will understand that. And for the maximum negative bending moment, what we will do, we will put that, see, this is the maximum negative ordinate. This 1.714 or 1.714. So if you put the 200 at this point, the 80 is out of zone. You get 200 into this ordinate 1.714 as 342. And but if you had put, you could also put the 200 here, right? Here also the ordinate is same, negative. But then what would happen? The 80 would come somewhere here and it would also have a positive part. So the magnitude of the negative element would have reduced. So you are placing it like this. We are placing the 200 here and the 80 outside this band. So this that's all for today. I hope most of the concepts have been and most of the concepts of the ILD has been covered. This is mostly what you can expect from the exams. And of practicing a few problems, you will understand this absolute maximum things are a little confusing, but they will get cleared if you just solve around 10 to 12 problems from any given book or anything. You will encounter most of the types that you will are expected to find. So, are there any questions? Okay, then I'll end the class now.